Assalamualaikum and hello to everyone. Today, my group and I will be presenting our project 3 that we study about influence of the block size. Okay, firstly, I will introduce myself and my group member. My name is Muhammad Ibn Shakir bin Ismail and my matric number is S62354. Then Muhammad Izzat Hakimi bin Roslan S63805. Then Nur Jalila binti Ottoman S63043. And lastly, Aina Nuraisha binti Shahrum S62719. Okay, firstly, I will tell you about the purpose of this project is to show the influence of the block size on the miss rate. Okay, we will study about the influence of the block size on the miss rate. Then for the introduction, okay, we study about the miss rate on cache are influenced by changing capacity, block size, and accessibility. Then the reason for the reduction of the miss rate is to understand the causes of the misses. As block size will increase, the amount of set in a very fixed size cache decreases, increasing the probability of conflict. Okay. This is for development part for the SMP cache, where we configure the SMP cache with this configuration. Firstly, the processor in SMP, we will put value 1. Then for cache coherence protocol, Messi is for cache coherent protocol is Messi. Then for scene for bus activation is random. Word wide is 16 bit. For main memory size is 256 KB. Then for cache size is 4 KB. For mapping, we using the fully associative, and replacement policy is LRU. We will conduct we will use this configuration on our SMP cache. Okay, next I will pass to my group member. Okay.
Assalamualaikum. My name is Muhammad Izzat Hakimi and I am the presenter for this part. For the task 1, the task asks about the configure the words by block using following configuration, which is for block size 8 bytes, 8, 16, 32, 64, 128, 256, 512 and 1024 for the block size 2048 bytes. For each of the configuration, obtain the miss rate using the trace file for CSP, EAR and COMP. The purpose of this task is to show the influence of the block sizes on the miss rate, and the hypothesis of this task is if the size increasing, then the miss rate will decreasing as well. For the hypothesis, we find out that the manipulated is the block size and the responding is the miss rate, and the cache size will be the constant variable.
So first, we click on configuration and choose multiprocessor. And then for memory organization, we choose SMP. And for number of processor, we choose 1. And then for Snoopy protocol, we set it as MESI, and bus aberration, we set it as random. Then click on configuration and choose main memory. So for worldwide bits, we set it as 16, and for this demonstration, I will choose 32 words by block. So for main memory size, we must constant the value. So we must constant the value to 256 KB, and then click OK. So next, we click on configuration and choose cache. So for cache size, we must constant the value to 4 KB. And then mapping, we must set it for fully associative, and replacement policy, we choose LRU. So next, we click on open memory trace and we choose trace, and then we click on PRG, and for our project 3, we must use 3 trace files, ESP, COMP, and EAR. So for this demonstration, I will show for the EAR trace file. So click on EAR trace file and then click on cache at view evolution. So there is two format, text format and graph format. So I will show both of them. So first I will show the text format. And then we click on execute and then we choose complete and click on continue. So this is the hit misses table. Okay, and then for next for graph 1 we must click on execute, complete and continue. So this is the graph format. So I think that's all.
Now, we will move to observation of the influence rate for words by block, and for the block size 8 byte, for CESP, COMP and EAR, we can observe that for trace file CESP, there are just a little increasing for block transfer and cache misses graph compared to COMP and EAR graph, while for the COMP graph, trace file and the cache misses is higher than the others. Now, we'll move to the observation for word block 8 and the size of the block is 16 bytes. For hits rate graph of CESP trace file, the percentages is increasing constantly compared to COM and ER hits rate graph that increasing occasionally. For next observation, we will moving on to the observation for words by block 16 and the block size is 32 bytes. For the graph observation, the CSP trace file showed that clearly increasing or constant process graph for block transfer and bus transaction, and also the cache misses graph compared to other trace file, which is EAR and COMP. For the next observation, we can see that there is no obvious change also in the block 32 64 bytes block sizes, which is show for CSP clearly increasing or constant process also for their graph for block transfer, bus transaction and the cache misses compared to other trace file also. For the next block sizes, which is 128 bytes and the word block is 64, we can observe that almost three of them has same graph for all trace file, which is CSP and ER and COMP, which are not obvious changes at all, which are there's no obvious changes at all of the graph, and we can see that we can observe that there are no obvious changes at all until word by block 512 and the block size 1024 bytes. And for the last observation, for the work by block 1024 and the block sizes is 2048, we can observe that the changes in EAR graph at bus transaction part, which is constantly increasing compared to CSP bus transaction graph that showed increasingly result.
Task 2. A. Does the miss rate increase or decrease as the block size increase, and why? B. Does this increment or decrement happen for all the benchmark, or does it depend on the different locality grades? C. What does it happen with the compulsory misses when you enlarge the block size? And D. What is the pollution point? Does it appear in this experiment? Okay, next we will move to the discussion part. The first one, does the miss rate increase or decrease as the block size increase, and why? The miss rate decrease as the block size increase, the same as the three different trace file. It is because to take advantage of special locality and to decrease compulsory misses. The second one, does the increment or decrement happen for all the benchmark, or does it depend on the different locality grade? The decrement happen for all the benchmark. It is also depend on the different locality grades, because all the data we observe have different amount of instruction, hit rate, miss rate, and block size. The next, what does it happen with the compulsory misses when you enlarge the block size? The compulsory misses will remain unchanged due to the block size increase, only causing more adjacent work to be fetched on each miss rate. Okay, next, what is the pollution point? Does it appear in this experiment? Pollution point is the point where it occurs when the block size is too big compared to Chache size. A bigger block size causes a higher miss penalty, and the system will take a longer time to load a new block to the next level. Pollution points do occur in this experiment for trace file, COMP, CSP, and EAR. The pollution point occurred at the words by block 512. Task 3. Does the increase of block size improve the system performance? The last one, does the increase of block size improve the system performance? No, because when the block size increase, the more time it consumes to fetch the block size to memory. This will end up with the increase of the miss penalty and consume more memory bandwidth. The higher the block size may reduce the miss rate, but the increase of miss rate penalty may lead to a loss in performance. Okay, next we'll move to the last part, the conclusion. In conclusion, surely fetching more bytes per block into Chache will decrease the odds that some part of the working set will be evicted because it resides in a different block. If the block size increase while keeping the Chache size the same, number of blocks that the Chache can hold will decrease. Fewer blocks in the Chache means fewer sets, and fewer sets mean that the collision and therefore misses are more likely. Of course, with fewer blocks in the likelihood that any particular block that the CPU need will be available in the Chache decrease. Okay, that's all. Thank you.